everyone. Today I will talk about something about the RT star anomalies. This work is an unfinished project with so many collaborators. Here's the warning. I'm sorry that this is my first physics paper, and I'm not familiar with a lot of details. And we failed to finish it before the conference, so some results are still preliminary. So let's turn to the introduction. You know that in the model, the charge current processes a B to C and a lepton with immune tau plus neutrino. It's mediated by a double boson with the interaction like this. We can see that the coupling is independent on the lepton flavor, so we call it is the lepton flavor universality. Define the ratio RT star like this. It is the ratio of the two branching ratios, B to D tau nu over D to D lepton, or replace D with D star. And using the model interaction, different groups will predict different RT and RT star number like this in this range. Testing the number of RT and RT star is a possible way to test new physics because if we can find some evidence different from the prediction, we will say that the lepton flavor universality is broken. This page listed the experiments from 2012. Different groups have measured RT or RT star with different methods, and we can have the average number RT and RT star. We can see that till now the RT is almost consistent with the model prediction, but for RT star there is still a 3 to 4 sigma tension from the model prediction, so it is worth it to give better predictions on RT and RT star. And there are also some related observables which can be modified by the similar interaction. For example, the RT psi, R and the tau polarization and the D star polarization. All these observables are all these observables are affected by the BC tau nu vortex, and there is also an important observable BC2 tau nu decay branch ratio. This is of course can be used by BC tau nu vortex, and the best prediction till now is about the limit is about 10%. In this work, we also update this estimation of the bound. Now let's turn to the effective formalism. This is the Lagrangian with the operators listed here, the vector type and scalar type and the tensor type. We assume new physics appear only in the BC tau nu interaction because for E and mu, the lepton universality is very good. For this interaction, if all the Wilson coefficients Ci goes to 0, it is the model limit. We can we can see that if all the coefficients go to 0, there is still one term left. It is the sum model operator. If the new physics scale is lambda, we can check that the operators V1, S1, S2, and the tensor can be generated from the dimension 6 effective field theory. But V2 is special. It can be generated at least from dimension 8 effective field theory. So the coefficient of V2 is expected to be suppressed more. Now let's turn to the updated form factor and the prediction. In fact, this is the main part of our paper, but I'm not familiar with this calculation, so we go through quickly. My collaborators performed a global fit using the data point from these two ways. One is from the lattice result with the large Q square. Here Q square is the invariant mass of tau and nu. Of course, the same for the lepton and the nu. For the data with the small Q square, they calculated using the icon sum rule, but I don't know what it is. With this global fit, we have a new prediction on the observables listed above, the RT, P star, P tau, FL. We can see that for RT star, there is still about 3.2 sigma tension from the experimental data. Okay, here plus means the experimental data minus the model prediction data. Now let's turn to the model independent analysis. Before the analysis, we re-estimated the BC to tau nu decay limit. Because this decay can be induced by BC tau nu vortex. If there is some modification in this vortex, it will affect the branch ratio like this. Here is the dependence on the CV V1, V2, and the CS1, S2. We can see that it is independent on the coefficient of tensor operator, but very sensitive to the scalar operator. That's because in the scalar contribution, there is no M-tau suppression. The sum value is about 2.4%. But if the scalar coefficient is large, it will significantly increase. So it is important to estimate how is the limit now. Let's turn to the estimation. Before this work, the best estimation of this limit is about 10%. By these two people, and they use the lab data with the effective current ratio defined like this. The U total nu plus FC over FU BC total nu. Now here the FQ means the ratio of a big quark hadronization to the hadron BQ. FC is expected to be less than FU and FD. So the FU over FC or FC over FU is a very important quantity in the estimation. In this paper they use the same method, but recently the FC over FU is directly measured by the RCB calibration. Oh, I'm sorry that I missed the overall factor 10 to the power 5 here, or equivalently there should be a factor 10 to minus 5 here. Oh, I'm sorry. So if we assume new physics only appear in the DC tau nu vortex, the DC to chip size mu should be the model prediction. Different predictions usually appear around 2%. So combine all these numerical results, we have the best estimation of this limit till now. It is about 6.8% at 90% confidence level, or 8.8% at 95% confidence level. And then we turn to the global fit analysis. We perform the chi-square fit for all the RDD star XI, ETO, and FL. All these observable. And the BC to tau nu current ratio is used as a condition. For the single operator cases, for example, we pick one operator once. A pure scalar or pseudo-scalar is already excluded at 95% confidence level. That's because the strict constraint from the DC to tau nu decay. This is consistent with the conclusion in previous work. And for a single vector or a tensor operator, it can be used to explain the anomalies, but for a single tensor case, it will predict a very small star projection. It is close to the 2 sigma exclusion boundary. For the V2 scenario, it favors large city violation. Let's turn to the implication to the Lepto-Quark model. We quickly go through this part. The Lepto-Quark is a scalar or vector which interact directly with the electron and the quark. There are 3 Lepto-Quark models can be used to explain the RD-SR anomalies, at least in this page, the S1, R2, and U1. We choose the Lepto-Quark mass about 1.5 TeV, which is safe at RC. and this is the interaction and the coefficient at the Lepto-Quark scale, and we perform the RG running to the B-Quark scale. The anomalous dimensions are already calculated in this paper. So we just use it to perform a running and then obtain the fusion coefficient at MB scale, and we can see that for all the three models, it still fit the data well, which means they can be used to explain the RTD star anomalies without predicting other anomalies. In the figure, green and yellow regions are allowed at 68% level and 95% confidence level respectively, and the light blue region is allowed by the BC for tau nu decay. And we can see that for the R2, the first figure favors a large equivalation scenario. For the other two Lepto-Quark models, if we assume real coupling, it still fits the data well. Let's turn to the summary. We updated the B2 D star form factor. This is the main point of this paper, but I just go through it quickly. And we updated the limit of branch ratio BC to tau nu. And we updated the model independent analysis with the simple operator, and scalar cases are excluded. And a single tensor scenario is, though it is still works, but it is close to the 2 sigma exclusion boundary of the D-star polarization measurement, and we turn to the implication to the Lepto-Quark models, and for the hard Lepto-Quark, the fitted data favor large equivalation. So that's the end. Thank you.
Could you show your result again? The two pages before.
Which result?
Yeah, this one.
Yes.
Where is the central value? I mean, where is the central point?
For the second,
For all.
it is about at this point.
Okay.
But it is
when you focus on the right hand the figure, it's almost the boundary, no?
Where? This?
Left handed figure. Left, on the left.
Left.
On the left figure.
This
The central points a kind of border.
This is a R2 and the S1 and the U1.
Ah, the different model.
Yeah.
Ah, okay.
Thanks, Peter.
For the Lepto-Quark model, do you have implications for
Sorry, can you discuss it?
or later?
Sorry. Because, yeah, we are behind the time. Okay, thanks, Peter.